I'm Dr. Samudrala Prashant Kumari, Government Institute of Chemical Engineering, Visakhapatnam. I am presenting my work title Waste Plastics Pyrolysis, Transforming Plastic Waste into Hydrocarbon Fuel. This study investigated the pyrolytic conversion of polyolefins like HDPE, LDPE, PP, and PS into valuable liquid fuels. Abstract plastic poses severe environment issue. Pyrolysis converted plastic waste into hydrocarbon fuel. Study explore a process optimizing and record reactor design. Introduction. Plastics first invented in 1862 by Alexander Parks are a high molecular weight polymer extensively used across industry. The Society of the Plastic Industry classify plastics into 7 types. Global plastic production has significantly increased from 1.5 tons in 1950 to 260 million tons 2007, creating a substantial waste management challenges. For instance, 2007, the US generated 30.7 million tons of plastic waste, while Europe consumed approximately 50 million tons annually. It will take New Zealand imported around 2.6 lakhs tons of virgin plastics in 2000, yet only 13.5% post-consumer plastics were recycled. Due to the durability of the plastic, the majority end up in the landfill, remaining for decades. With increasing the plastic consumption and limited landfill space, alternative solutions such as biodegradable plastic and advanced recycling technology are being explored. Pyrolysis offers a viable method to convert the plastic waste into fuel, addressing both environmental concern and energy shortage. Economic value. Plastic pyrolysis not only conserve land resources but also provide alternate energy source. Converting the plastic waste into fuel could reduce the reliance on fossil fuels import. Pyrolysis derived fuels are sulfur free, preventing air pollution from sulfur dioxide emission. Pyrolysis of plastic material. Pyrolysis of plastic material. Pyrolysis is the one of the method you are using, that is thermal decomposition process is an oxygen-free environment that breaks plastics into smaller hydrocarbons. The pyrolysis reduces waste accumulation and prevented toxic emission. We are choosing HDPE, LDPE, PP, and PS are particularly suitable due to their high calorific value when you are compared to traditional fuel like LPG and diesel. Some commercial pyrolysis plants utilize a catalyst to improve the fuel quality. Objects. When you're choosing an objects, the finally oil yield and focus on HDP, LDP, and PPM, PS only. 3 stages you are choosing. One is thermal cracking, process and react optimizing, and continuous of operate design. Objects of the investigation. The study aimed to optimize the pyrolysis process to a maximum oil yield and design a semi-commercial continuous pyrolysis operation. Focus was on HDPE, LDPE, high density polyethylene, low density polyethylene, polypropylene, polyester, which constitutes 70% of packing plastic. PVC and PET were excluded due to hazardous emissions. The study was undertaken and was conducted in 3 stages: understanding thermal cracking. The second one is optimizing process reactor design. Third one is developing continuous pyrolysis apparatus. When you see understanding thermal cracking, identify key factors affecting pyrolysis and product quality. That is temperature, heating rate, plastic type, and catalyst and plastic interaction. Second one, optimizing process reactor design, that is gas chromatography and mass chromatography. When you see the developing continuous pyrolysis operator, that is construction reactor, permanent reactor, that means to convert LDPE and PE, PEP, PS mixer into gas and liquid fuel. These 3 designs are you are using. Pressure. When you choose pyrolysis method, in that pressure is one of the factor to influence the reaction. When you see Higher pressure raises the boiling point, promoting further cracking of heavy hydrocarbon, leading to increased gas yield and reduce the liquid yield. Reactions are four stages: reaction, initiation, propagation, termination. Initiation, propagation, hydrogen transfer, termination. Initiation, polymer chains break. Higher molecular weight polymer breaks into free radical. Propagation, it further breakdown reaction. Hydrogen transfer, in this reduce the polymer. High molecular weight polymer reduce smaller molecular weight. Termination, finalize the reaction by forming stable hydrocarbon. Reaction kinetics are four stages, and reactors are batch, semi-batch, and continuous. Bed types are fixed, fluid, screw clean. These are the reactors. Class based on the reactor bed types: fixed, fluid as bed, screw clean. Resistance time: fast pyrolysis or slow pyrolysis. Fast pyrolysis, short resistance time. Slow pyrolysis, longer resistance time. Fast pyrolysis, the short resistance time favor liquid yield. Slow pyrolysis, longer resistance time promoted tar and char formation. Adjustment in feed rate, gas flow, discharge rate helped optimize resistance time for desired product distribution. Catalyst also influence in the reaction in pyrolysis method. One is homogeneous catalyst and second is heterogeneous catalyst. Homogeneous catalyst, Lewis acid, that is AlCl3, and heterogeneous zeolite, clays, and metal support catalyst are using. Chain cracking mechanism: random cracking, chain strip cracking, and chain cracking. Random cracking, we are using polyethylene, polypropylene, and polystyrene. Chain strip cracking, side group detach first. End chain cracking, degradation of start from chain ends, yield smaller hydrocarbon. Higher molecular weight polymer will breaks into the smaller carbons. Kinetics. Kinetics of plastic pyrolysis. Reaction rates influenced by catalyst, reactor types, and plastic composition. Arrhenius equation govern the reaction kinetics, where it is active energy is the free exponential factor is the gas constant temperature. Energy analysis. Energy demand calculation depend upon the polyethylene and pyrolysis method, that is endothermic reaction. The total energy required for pyrolyzing 1 kg polyethylene is approximately 1047.62 kilojoules, with a net energy gain approximate 42.3 mj per kg. Conclusion: plastic pyrolysis present a viable waste management energy recovery solution. We are using plastics in a four-stage plastic processing consisting four stages: initiation, propagation, hydro transfer, and termination stages. We are using high density polyethylene, low density polyethylene, polypropylene, polystyrene are useful to convert the plastic waste to hydrocarbon fuels. These are the reference you are using: Gupta OP, Nag PK, Anaj G, Chemical Kinetics, Smith and Vanes, Chemical Engineering, Dynamics, and Google search. Thank you, one and all.